So, so now we switch to one more topic that I should cover. It's about neural networks. Yeah, so we talked a little bit about classical machine learning. So now let's get to neural networks and to non-classical machine learning. So neural networks were basically inspired by some biological ideas. So people were trying some sort imitate the real neuron, and we're hoping that if you imitate it good enough, you can get something meaningful out of it. The modern neural networks, basically as imitation of biological networks, are quite poor from the point of view of a biologist. But they can perform many things that are quite astonishing to us. So basically, they are very useful, and despite that fact that they don't basically resemble their biological counterpart, they are still very useful, and we want to use them even more and more as time progresses. Okay, so what is the idea behind all that neural networks, and why are they called this way? So as I told you previously, once again, we have that source of 2 points of view, a mathematician's and engineering point of view. For example, from mathematician's point of view, we are searching for the function that is the closest function to some targets. So to the function that gives us always the result we want. In case of neural network, we have just the same thing. The only difference is in a way we are constructing our models, our model functions. We are basically constructing them as some sort of Lego. So we have building blocks. These building blocks are called neurons. What is a neuron for machine learning scientists? That's some sort of, as you see, some sort of function. It takes a number of inputs. Here I showed you 3 inputs. Of course, it may be much more or even less. It combines them linearly. So you take each input, you multiply it by some sort of weight. It's called weights. They are stored in that neuron, and when it gets its input, it multiplies it by that. Adds them all together. It may add some additional value called bias or bias term. And after everything is added together, it puts them through some sort of function called activation function. So what is activation function? Here are a few examples of activation functions. For example, the sigmoid function. It takes a value and tries to make it plus or minus 1 from that value. If it's very positive, it makes it close to 1. If it's very negative, it makes it close to minus 1. Or to 0, I mean to 0. Or it's tan h, so hyperbolic tangent. It makes it plus or minus 1. Very often now used ReLU. It leaves leaves the value as it is if it is positive, or makes it 0 if it's negative. So all negative values are set to 0, all positive are left the way they are, or leaky ReLU, or so on. So there are many activation functions. This basically, this architecture was inspired by living neurons. So people suppose that living neuron is getting some inputs from its dendrites, and when this input combined is more than a certain threshold, it fires an action potential. So something happened. And they were trying to imitate this behavior with this sort of simple model. So they were taking some inputs, they were combining them and putting them through the function that should imitate that action potential when it passes some sort of threshold. Of course, if you get into details, you will see that it doesn't quite resemble a biological neuron, but let's get with what we have because it works, so why not? Okay, what is a neural network? So neural network is basically a collection of such neurons. So we are taking all that neurons and we are wiring them together to get something like this. This is a very simple example, just few neurons, but this is already a small neural network. How it works? First of all, you have some input. So these neurons, despite it's not shown, they are taking some input from the, let's say, external world. So you are setting your input data into these neurons. They are processing this data and passing them to subsequent neural layers. We are collecting, basically, it's really hard to track each neuron. So we are collecting this neuron into some sort of stacks, and we call them layers. So we are stacking them together to get a layer. Now what we do, we are these layers are passing information. They take it from their inputs, they are processing it, passing to the next layer. And the last layer, it will be called an output layer, and you will get your result, whatever you expect from your neural network from this output. What results may you expect? Well, that depends. So it may be some sort, I don't know, if it's a classification problem, you will get some numbers that signifies a class you are expecting your input to be in. If, I don't know, if you are transforming somehow your image, so for example, you're giving some photo on the input and you are expecting some different image on the output. So I don't know, some background removal, for example, or whatever you think about, you will get everything from the output. All the rest layers are called hidden layers. So user does not see them, despite there is much more hidden layers than all these inputs and outputs. So modern neural networks, they have so many layers that they are even combined into blocks, because you can track even an individual layer. So you combine few layers into blocks, and then you build your neural network from that blocks. Or you can combine that blocks in something even bigger and bigger, because it's really, they are so large. Modern neural networks are so large that it's even hard to keep track of everything that stays inside of that neural network. So what happens there? Once again, I remind you that every machine learning problem is some sort of minimization or maximization problem. So in case of neural network, you are basically minimizing some sort of cost function or loss function or whatever you call it. In most cases, it is performed by some first order method. We have already seen this presentation. These are different first order methods. They are all available in TensorFlow. So if you did something with neural networks, you were probably using one of them. And they are minimizing something. But what are they minimizing? So how that works? I want to try to give you a quick example how this minimization works, to get some, I don't know, some general idea what happens. So, okay, here is a very simple neural network. It gets some inputs. So each neuron here gets 2 inputs from the outside. Then it processes them with some functions. Here are function A, B, C, functions X, Y on the second layer, and function F on the last layer. So this is our neural network. We pass some inputs, we get some outputs from this small neural network. What we do then? Then we may add some more functions to estimate whether this output is good or not. That may well depend on the problem you are solving. So for example, you are passing, I don't know, some photo inside, and you want to get class of that of that photo, whether, for example, whether it's a photo of a cat or photo of a dog or whatever. And you can use, well, if you remember the first lecture I gave, you can use that ideas to construct some sort of function that estimates how good your network performs. That will give you some number how good it performs, but it's not enough. Well, basically everything this combined together constitutes one big gigantic function. So you may think of it as a function that gets some input in here and gives you how good this neural network performed. So that's a large gigantic function. And you want to minimize this function with respect to parameters. What are parameters? It's basically these quotients that we are keeping in our neurons. So this W and these biased terms. So these are the parameters. We want to minimize with respect to these parameters. And what we have this sort of gigantic function built from these neurons. So that's our problem. What do we want? We want to perform some sort of gradient descent or whatever. So some sort of first order method. What do we need for that? We need a gradient and we need value of the function. That's all what we need. Okay. How do we get all that gradients? Let's check it more closely. Here we have a function that we calculate in the last neuron. So the problem is the following. I want to get a gradient with respect to all parameters that are inside this neural network. But it's built from these tiny blocks. And I want to somehow to calculate all that gradients without writing my function explicitly. Because if I'll try to write it explicitly, that would be a disaster. The number of parameters is enormous. It's unimaginable. I don't know, very old network, AlexNet, had 1 million parameters. So of course, modern neural networks may have, I don't know, billions of parameters. Well, very, very many parameters. So you don't want to do that. You don't want to write this function explicitly. That's impossible. So how do you do that? You use a chain rule. So everything is based on a chain rule. Let's try to check it, how that plays out. So here is the function I calculate on the last layer. This is a neuron. It has its parameters, W1 and W2. So here they are, W1, W2. With respect to W1 and W2, I can find partial derivatives of f with respect to W1 and W2. They are basically, I can get them. What do I mean by first order method? I mean that this is a method that uses as its inputs first derivatives of a function. Second order method, like Newton method, will use second order derivatives. So you will need to build a Hessian matrix. So all second order derivatives. And you can have a zero order method. I showed on some of the previous lectures. So for example, Nolder-Mead method that does not use any derivatives at all. It uses only values of the function. So the first order just means that we use first order derivatives. Okay, so W1 and W2, we are okay with that. So we can calculate that. And as we know, analytical expression for the f, when we were building this neuron, we know how we build it. So we know the analytical expression. We, of course, know analytical expressions for these two derivatives. So we can calculate them at some point where we are, and we can get numeric values for these derivatives. That's pretty okay. But now what we do next? We need to do something with these neurons. They have their own parameters. How do we do that? So these are okay. W1, W2 are okay. What we do with all the rest things? To minimize f, we basically need a partial derivative with respect to x and with respect to y. But this x and y were basically inputs into this neuron. You can't just explicitly write derivative with respect to them because that will imply writing all this function in some sort of explicit way. So you will get a very large function. You just can do that. But we need only numeric value. So what do? We pass these values to the previous neurons. And then we process these values on that previous neurons. How do we do that? We use chain rule. When we pass when we pass them to the previous layer, we can write that df over dv1, v1 is the parameter of that previous layer, is basically df over dx multiplied by dx over dv1. And dx over dv1 basically can be calculated. So we were just passing these parameters to the previous layer, and here what we get. Here are two parameters that we are combining together. You see that they came from one neuron here. So this is a plus sign between them, and they all are multiplied by delta beta. So what I'm writing here, it's a small change of f when we have a small change in any of the parameters of the neural network. So all these deltas are some sort of tiny nudges. So when you are a little bit just changing some parameter, what do you expect? How do you expect to change your delta f? So quotients before them are basically values that you will see in your gradient. How to calculate df over dx. If I have an analytic expression for f, I can basically I can basically take these derivatives with respect to x, but I need derivatives with respect to v1 and v2, because v1 and v2 are the variables I am minimizing. Well, basically, yeah, I think I said a little bit wrong thing, yeah. Because we can calculate df over dx, we can calculate df over dy. That's okay, because I have analytic expression for f from xy. I'll show that in the, well, why don't we see it in this slide? Here is an example. Here is the function f. It's just randomly chosen, so it doesn't make any big sense. Here are parameters w1, w2, and x, y as inputs. And as you see, I can take a partial derivative f with respect to x, partial derivative f with respect to y, and partial derivative f with respect to w1 and w2. But what I actually need, I need partial derivative of f with respect to parameters of the other neurons of v1, v2, and so on. So I pass these values, I calculate these values as numeric values. I pass them to the previous layer. It's called back propagation. So what we are now talking about is the back propagation. I pass them to the previous layer, and then I can insert them into the equation for partial derivatives with respect to parameters on this layer. So that's what happens. Now, there are parameters that are inherent to these neurons, like say here V1 and V2. So they are basically kept in this neuron, and we can calculate partial derivatives with respect to them. And now I can multiply df over dx by dx over dv1, and I will get basically df over dv1. So here is the point I got my derivative with respect to parameter v1. And of course, the same way with respect to v2. But we still have two inputs, a and b. I can calculate df over dA and df over dB the same way. I have df over dx. I have dx over dA. So why not get df over dA? No problem. No problem with df over dB. But these are inputs. You can't minimize inputs. You minimize with respect to parameters of your neurons. So you can just say, I don't like this input and change it. You can say, I don't like this parameter. Let's tune it. Let's make it somehow better. So once again, I use what I can use, and I pass to the previous layer what I can't use. Please note this plus sign. this neuron was passing information to these two neurons, to this neuron and to this neuron. So when we calculate, when we will be calculating derivatives here, they both will influence on this neuron. In formulas, it looks like they all are near the delta B. So they are all influencing this delta B. And we are combining them together. You can basically check that with some sort of chain rule and so on. It's really, it can really be checked. It's really simple, but a bit tedious, yeah. And once again, we pass everything to the first layer. On the first layer, what we have some derivatives with respect to parameters of this first layer and derivatives with respect to its inputs. Since inputs cannot be changed, so we have no influence on these inputs, we say that this delta I1, delta I2, they are equal to 0. So you can change parameters, you can change inputs, of course. So we set them equal to 0. And what is left? We plug in to our equation. And at the end of the day, we have a really, really big expression for our delta F. And this is basically defining us the gradient. So all these quotients staying before delta some parameter are basically components of the gradient vector that we can use. So now what we have, what are the rules? How does single neuron operate? It gets some inputs, let's say xy, calculates function f, and gives you some output that. That's quite simple. On the back propagation, what happened? That was forward propagation. So it's just normal operation of the neural network. Back propagation. He gets gradient from that neuron. He passed his information to, calculates some partial derivatives with respect to its local parameters. And that will help to update the gradient vector and update the parameters when it needs. And then he passes to the previous layer partial derivatives with respect to its inputs, so that neurons on that previous layer can take them in, can multiply them with what they need, and get partial derivatives with respect to the parameters they keep inside. So that's the way it works. So forward propagation, you're just calculating the function along the way. So you are getting inputs, calculating output. Which functions I showed you previously? You make a sum with all that. Mostly you take a sum with all that coefficients, and then you apply some activation function. When you are back propagating, you need to minimize all that function. To minimize it, you need to have all that partial derivatives. To get all the partial derivatives, you do the following. You accept the partial derivative from the next layer. You calculate partial derivatives with respect to your own parameters, and you pass partial derivatives with respect to inputs to the neurons that gave you that input. If there is a case that neuron passed his output to two different neurons, it combines them with just adding together. How z depends from x and y. Z is a result of this function. Most cases, you will have something like this. You will get x, y as inputs. You will combine them with some quotients, some wx and wy plus some bias term, and then passes through some sort of activation functions. For example, I don't know, ReLU, let's say. So if it's bigger than 0, it will do nothing. If it's less than 0, it will be 0. Of course, there's a question: how do you calculate derivative of this ReLU? For negative values, you set it to 0. For positive values, you set it to 1. When it's 0, it's a bit tricky, but anyway. So that's the most cases that will look like something like this. Here is a small example. We're really scarce on time, so I won't get really detailed through. I just wrote some functions in. These are not some actual activation functions or something like that. It's just some random garbage I put in. I just wanted some functions that I can easily take derivatives from, and that will combine some sort of inputs and parameters. And you see that when I am defining some sort of function that acts in this neuron, I can immediately calculate its derivatives. Everything should be done in some sort of analytical form. So I should know how do I calculate partial derivative with respect to inputs and with respect to parameters. Basically, as you might guess, inputs of the function parameters are barely different. Well, are almost the same thing. So it's just the matter of how do you call them. Because anyway, everything is combined into this, let's say, sign from v1 times a plus v2 times b. How do you say which one of them is you called parameter, which one of them you called an input? So it's basically the same thing. And just for us, we know that this we will get from the previous layer, and that we will keep here and store somehow locally. So we will call them parameters because we store them locally, and that will be input because we get it from previous layer. But for the function itself and for its derivatives, it doesn't basically mean anything. So what can we do? We find all that derivatives, we can find them. So now when we do forward propagation, here I will remove some unnecessary derivatives because these are inputs. As you know, inputs, we can change inputs. So I remove them. Now, what we do, neural network, when we start training, we are initializing parameters. Well, you will see that when you will train any neural network, you will see that there should be some sort of initialization algorithm, and you will choose one of the few available to you. So that's okay. In most cases, you will take some random numbers to initialize your neural network. I do the same way here. Initializing everything with zeros is not very good idea, as you might guess. So most cases you take something random and then you just go with learning and all that minimization. Now what we do, I have values of these parameters. I have analytical expression for all the function and their derivatives. So nothing prevents me from calculating. If I get some input, here are the numbers as I get as an input. Nothing prevents me from calculating these values. I have a function, why don't I calculate it? I have expression for derivatives, what's the problem to find it? I find it, I pass my outputs to the next layer. When these outputs came to the next layer, there is no problem to calculate everything, function and derivatives. Now I have it. Now I pass it to the next layer. As you see, we have analytical expressions right now, right here. So I pass here input values and I get everything. Okay, so now I have my function. Suppose that I want to minimize this function. So now I do back propagation. So I need to move backward. I need to move backward to get the gradient because I'm using some sort of first order method. So I need value of gradient. Okay, what do I need for gradient? These expressions are written already with taking the chain rule into account. So whatever we were calculating previously, I put it into one vector and you see it here written explicitly. Now, some of these derivatives, for example, with respect to W1, W2, are present here in the gradient and I have already calculated them. So I can plug them in. Okay, small part of gradient is available. So that were the parts with respect that are connected to delta W1 and delta W2. Good. Now I pass my derivatives to the previous layer. I pass them here. I can calculate all these things. I multiply basically what I have here. So I can get derivative delta df with respect to v1. Because this dx, they somehow cancel. So df over dx times dx over dv1 gives me df over dv1. And that's the thing I can already plug in to my gradient. So I have a few more components. Great. Now I pass to the previous layer that numbers I have calculated once again, backward propagation. So it's so it's reasonable. Okay, I pass them here. I can once more perform that multiplication and get values for all that derivatives I needed. And right now I have my gradient. So I can perform step of gradient descent. I have gradient, I have values of function, nothing prevents me. I can do gradient descent step. And I can change now my parameters the way that makes this function minimal. So that's basically what we do and how neural networks are trained. Okay, now a really, really quick run. Simple neural network, how it looks in practice. So here is the MNIST data set. So it's a bunch of handwritten numbers that are used for classification problems. I want some neural network to perform, let's say, classification, how it looks like. So here is a TensorFlow example, very, very simple. I am adding some layers. So for example, let's see this output. So for example, some convolutional layer. It's some sort of, once again, some sort of linear operation on the input and some sort of activation. As you see, I'm using hyperbolic tangent here as activation function. These are basically parameters of that linear combination I'm using, so don't bother with it if you don't know what it means. So this is layer one. It contains a few of these neurons. I'm using some other layer, so-called average pooling, that takes some, once again, it takes some inputs and it does some activation. One more layer, it basically does almost nothing, just reshapes the data I'm using. And the last layer, I'm using dense that will leave me with some numbers that represent basically the probability that given input should be classified as certain class. So I have 10 outputs and I have 10 numbers that that are basically that probabilities. And I will choose the biggest one of them as the result of my neural network. So I will not get through all these details. Of course, on top of that, this is result we do. We should somehow estimate how good is this result. It's performed with a loss function that we call categorical cross entropy. If it doesn't say you anything, just don't worry. It just measures when my neural network says, I think it's 50% of class 1 and 10% of class 2 and so on, so on. It combines all that numbers. It takes input that it should be, for example, class 9, and it tells me this result is that bad. So for example, it gives me some measure how bad is that result. So if my network guessed, it will give me some smaller number. If it missed, it will give me some higher number. If it missed just a little bit, so for example, it was thinking that maybe that result, but some other class was just a tiny little bit bigger, had just tiny little bit bigger probability, it will maybe give me some smaller number and so on. So I'm training that. Here is the confusion matrix that I can get from my neural network. So it's, in some sense, it's classifying. So really simple network, it's classifying me that 10 classes. And as you see, it's almost diagonal. So it's really good classifier. Well, in some sense, if you think that there are only 3 layers, that's pretty okay. Here is what happens to on the each layer. So here is the input. This you get as a raw input to your neural network. These are 6 neurons that are living on the second layer. That's what they see. So that the result of their action on this input is getting to each of them, and they are acting on that input. Then we have the next layer. I call it average pooling. This is result from that layer, and then you get output. These are the numbers that this thing is outputting. As you can see, 9.99 times 10 to the minus 1 is the probability that this is the number 0. So it's it classified it correctly. Okay, I won't show you this thing.
We have
10 minutes we have. Okay, now I'll try just very quick recap 2 architectures, or maybe 1 if I don't have time. So I was asked to tell you what is a neural network and architectures like variation autoencoder and generative adversarial network. So let's try with autoencoder. Let's see, this is a simple autoencoder. So what is the idea? I am building a neural network from a set of layers. let's consider that that I am making each next layer a bit smaller than previous. So I'm using a less and less, some lower and lower number of neurons on each of the next layers. I get to some point where there is not so much neurons, and then I am trying to make layers bigger, bigger, and bigger. It looks like on this picture. Why am I doing that? The interesting thing is, if I am giving some input to this network, and I am demanding, as my loss function on right, I am demanding that it outputs the same thing as this input, this would mean that all the data that I have on the input should be perfectly restorable by the data we have on this really tiny layer. So what that? That's dimensionality reduction. So we have this input can be considered as the vector of some multi-dimensional space. Even be it a picture, you can just stretch it in some long vector, and you can say that this is a vector of some many dimensional space. I don't know, hundreds, thousands of coordinates, millions, whatever. And it can be squeezed into few numbers, or maybe not a few, maybe 100 numbers or whatever this layer size is. And then it can be still unsqueezed, and you get the initial thing without significant loss of information. And that is really good. This is somehow similar to so-called PCA, so principal component analysis. Well, basically one layer of variational autoencoder linear will do the same thing as this principal component analysis. I want to show you just a quick example of that. So what it means. So here I have points in 2D space. Both coordinates are basically features, but these points, they lie on something that resembles a straight line. So, so 2 coordinates is too much to describe these points in some sense. If I choose wisely a new coordinate system, let's say this way, I can basically neglect one of the coordinates and squeeze all the information into one number. Of course, this is a very extreme case. I'm getting from 2 coordinates to 1 coordinate. But there are many cases you can get from many coordinates. You can't even imagine, I don't know, thousands or billions of coordinates into just a few that you can even draw and get some insight into that. Let's check how that looks like. Here is a small autoencoder. Once again, I have no time to get through all of this. This is the encoder part. This is the decoder part. So these layers are getting smaller and smaller and smaller. You see 30, 32, 16, 8. Here are, I guess, 3 or something like that. And once again, we get back 4, 8, 16, so on. What it does, let me show you. The MNIST data set, it takes an input and it tries to recreate it, just pushing it through that bottleneck. So as you see, number 4 is almost recreated as number 4. Number 6 is almost recreated as number 6. 1 is almost as 1. But they were all pushed through that bottleneck that contains only 3 numbers. And if I draw now the 3 numbers, and I will give them a color based on what class they are from, you can see that this space is in some sense meaningful. So you see that zeros are compactly living somewhere here. That, I don't know what that, 6s or whatever are living here, and so on. So this space is useful for representing our data. I see some insights into our data. It is useful for classification. I can squeeze all the data into 3 features and use that 3 features to classify it further. That's great, and so on. So that's the case. The second thing, I can use it to make something with noise. Here you see the same example as previously, but instead of the input, I'm giving input plus some noise. So I'm basically distorting my input. But when getting through that bottleneck, my neural network tries to get away with that noisy input, and it throws away the noise, keeping the basic information. So it's really good. You can make your image a bit better when you are putting it through that bottleneck. Okay, what about variational autoencoders? Basically, it's an autoencoder, but with one additional feature. Right now, I showed you that we can squeeze initial information into some space that will represent some sort of parameter, some smaller with smaller number of dimensions. But we don't know whether each point of this space is meaningful. It may happen that some points of this space, they represent something meaningful. For example, you have a square, a circle, a triangle. They were represented at these points, and these points are decoded once again as a square, triangle, and circle. But not each point of this intermediate space is meaningful. You are taking some random point and you get something random that you didn't want to get. So variational autoencoder is a way to force not only recreate the initial data, but actually make sense of the whole parameter space that we have here, or at least some compact subspace, so that you can navigate through it and always get some meaningful result. How do you achieve that? You are basically moving from the idea of generating the exact point in this space to the idea of generating some sort of distribution, or you are giving some parameters of the distribution. It's not such a big shift of point of view as you might think. So, for example, you can think about some, I don't know, some normal distribution. You can still get a point, just making it very, very picky. So you make a, for example, small sigma parameter, and you set mu parameter, so its mean value to be at this point. So it's obtainable. But you add something, so you get these distributions, and of course around this point you will get something meaningful. So you will get some triangles around this, some squares, so on and so forth. But they are still not covering the whole space, and they are still not constituting some compact subspace that you want. So what do you do the next? You add something additional to your loss function, and you are demanding all these distributions to be first not too local, so not to be too, let's say, so spiky, and you want them to be somewhere near one place. So you want to collect them together. How do you do that? You basically want them to resemble the unitary Gaussian as much as possible. So you are driving them towards their means towards 0, and you are demanding their sigmas to be some significant. Of course, you will never ever make them to fully sit at 0, because that will be not so good. But you can drive them close enough so that they start overlapping, and this part of the space, so any point of this part of the representation space will be meaningful. You will generate something out of it. So, for example, you see here circles, triangles, squares. When you take this point, you get something like triangular-like, but with some rounded angles, and this is good. So, so this part of the space is meaningful. So you can now use your decoder as a generator of some meaningful things, setting as an input any point of this part of the representation space. So that's really good. Of course, there are some mathematical things that you should take into account. You should ask, how do you get back propagation? Because when you train it and you set all that demands, you should perform sampling, but it's really technical. I think I will leave it out. And now I think I should finish up. So unfortunately, we don't have time to get through generative adversarial networks. It's really nice thing. They can, for example, transfer style, as you see. Nice example, but anyway, they convey some ideas I have provided to you, but just they have generator and discriminators that are basically pulling the rope, each one, and you get something that can generate you some meaningful result by getting some random parameter from representation space. So it's a bit similar to the previous theme. Okay.
Thank you. Thank you for the lecture. There are a few questions in chat, and I think that there was few questions about how to calculate derivative df per dx.
I think I have addressed that part when we were considering the example. So that was the input of the function f we had previously, and when we have analytical expression for f, of course, so we can find that sort of derivative. It was somewhere. For example, it was here. Why not? Let's get a little bit before. So here is, for example, the function f. You have f of x, y with parameters w1, w2. It's some random function, I don't know, w1 times e to the x plus w2y. And nothing prevents you from taking partial derivative with respect to x and get something like this, w1 times ex plus w2y. Or with respect to y and get the same, but you get w1 times w2. So it's really okay. But the thing is, the problem is that we don't need derivatives with respect to inputs. We need derivatives with respect to parameters. So we should somehow convert this thing to derivatives with respect to parameters on the previous layers. And the only way we can do that, we should pass them to the previous layer so that neurons on that layer can use the chain rule, multiply everything together, and get derivatives with respect to their internal parameters. So that's the only way. Because you see, on this previous layer, you don't have df over d something. You have dx over d something. We don't want dx over d something. We want the whole df over that parameter. So that's basically the main concern and why we need all that backpropagation.
I have a short question about area of applicability. So we have SVM classification method, and we have, for example, classification with neural networks. When do we apply, for example, SVM? When do we apply neural networks? Like, what's the
really good question. Yeah. So SVM we will apply in cases when we have small data sets or small number of features. So it's if your data set is really small, you will probably get some troubles with applying neural networks. So I wouldn't expect them to work too good. But SVM still can handle that. If you have a large data set, if you have a large number of features, you should probably go with neural network because I wouldn't expect SVM to make it through too large data sets. So you basically should orient first of all on the size of the data set. The second thing you might want to consider is the device you are running your program on. So if it's something embedded, if it's some tiny processors and you don't want some resource demanding applications to run there, you should probably go with SVM because I don't think you'll be able to run some heavy neural network on something really tiny on some embedded devices. So that's, I think there's 2 points to consider. So the size of the data set, the number of features, and basically what device are you using?
Is the neural network other neural network using only for the classification problems, and there are some?
There are many neural networks that you can use for classification problems with many different architectures. Well, the first one that comes to my mind is YOLO, you only look once. But there are many other. You can check them on the internet because it's a really popular problem. So you often get some classification problem, starting from something like, I don't know, you give a photo and it tells you this is a chair and this is a human and this is something else. And ending some, I don't know, some industrial applications when you are trying to build a robot that basically throw the waste, let's say, some bad details from the conveyor belt. So there are really many such networks.
Okay, thanks.
Okay, so seems no other questions, I guess.
Yes, thank you very much. So now we have a 5 minutes break, and then we will start with a lecture by Dr. Andrei Semenov. So it will be in 5 minutes. Thank you very much for the lecture, and thank you for attention.
Okay, thanks everyone. Goodbye.